Hello and welcome to lecture 8, part 2. In part 1 of this lecture, we talked about development of design equation in terms of heat transfer coefficient of condensation for a horizontal condenser. And we talked about two special cases where in one case the condensation was happening in the shell. And then the second case where we looked at when the condensation was happening inside the horizontal tube, and we developed this equation for that. So now let's have a look what will be the design equation if we have a vertical condenser. Okay, so here we assume that we are in a vertical surface or vertical condenser where the condensation is happening inside the shell. It means that the condensation is on the outside of the tube, and as such we can consider Nusselt equation again for film-wise heat transfer coefficient of condensation that is slightly different from the equation before. And you should have covered this equation in phase exchange heat transfer, and where we have L is the length of the tube and delta T is the temperature between the condensate film. Okay, so this delta T is very difficult to measure because it is very difficult to measure the temperature of the surface of the tube inside the shell and tube heat exchanger. So we have to find a way to get rid of this delta T. And just like the analysis we did for a horizontal shell and tube heat exchanger, we are going to use the same procedure to get rid of delta T. So let's say we consider a system that is under steady state condition and a tube bundle that has NT numbers of tube of length L. So if we try to write the rate of heat transfer for this system, we can write that Q is equal to m dot HFG, that is the latent heat of condensation. And if you expand this term in terms of the heat transfer coefficient of condensation, you can write it like this, and then we can expand area as pi dl. And if you notice here, because the condensation is happening outside the tube, that's why we are using the outside diameter of the tube here. Okay, so if you find the value of delta T from this equation that is here, and then feed into this equation here, you get this final equation as Hc is equal to 1.35 times this part of the equation here. Okay, so this is again an equation that is based on ideal system. Okay, and where we are considering that the condensation is happening in the shell. Now let's look at what will be the situation if the condensation is happening inside a vertical tube, inside a vertical condenser. So again, here we start with Q, the rate of heat transfer for condensation, and then we expand the area term, but now we are using pi dIL. So di is the inner diameter of the tube because we are using or we are considering that the condensation is happening inside the tube. And again, you will calculate the value of delta T from this equation, and then you feed into our main equation, and this time you get this expression here, that where the heat transfer coefficient of condensation is a function of properties of the system and the inner diameter of the tube. Now these equations are again just like the case for horizontal condenser. They are developed for laminar systems where the condensation is happening and flowing inside the tube in a laminar flow, and you can use the value of Reynolds number to make sure that you are in laminar flow, and then you have to use this equation here where you are considering the diameter of the inner tube and the number of tubes. Okay, so what we looked so far is that you can have a situation where a condenser can be in horizontal arrangement, and then you have developed the equation for condensation in the shell and the condensation in the tube. And if you remember that for the case of condensation happening inside the horizontal condenser, when it was the shell case, we looked at that the condensation is happening on the tube, but we also considered the correction NR due to the fact that there is dripping that is happening from this tube when it is a horizontal condenser. While for the case of a vertical condenser, we are not using this correction factor NR. As you can see, it's not here. The reason being because when you have a vertical tube and the condensation is happening here, it is not really dripping because it is just maintaining a film and then flow under gravity. Okay, so as such, we don't need a correction for this dripping effect that was the case for horizontal condensers. Okay, so that is slight different in equations when you are looking at a horizontal condenser and a vertical condenser. And another difference is that when we looked at a horizontal condenser having condensation inside the tube, we said that there can be accumulation because of the condensation of the condenser, so of the vapor, and we multiplied over Hc with 0.8. But for the case of vertical system, if the condensation is happening inside the tube, we are not going to use this correction factor of 0.8 because again we are not going to have any condensation because of the gravity effect. So if the vapor is going to condense, it is just going to move down because of the gravity effect. As such, we are not going to need to use a correction factor. Okay, so the expression that we developed for Hc in the previous slide give you an average value of heat transfer coefficient of condensation for the entire surface. And if you remember, when we were doing the analysis, we considered that the whole bundle is involved in the heat transfer, and as such, we have the entire surface in the system. Now, that value of Hc actually is important when we are looking at the design of condensers because we need the value of Hc to calculate the overall heat transfer coefficient. And once we have the overall heat transfer coefficient, the rest of the design of a condenser is just like a routine heat exchanger like we did in lecture 7. So let's have a look at that, how we can use that for condensers as well. So let's start with our main heat transfer equation, that Q is equal to UA delta T Lm. Okay, and in this case, all the heat to the system is coming from the latent heat of condensation. So that's why these two equations are equal. So we know U is the overall heat transfer coefficient, A is the surface area of the heat transfer, and then we have delta T Lm, that is the mean driving force. And the U, the calculation of U can be done exactly in the same way like we did for heat exchangers by using this long equation where we consider the effect of heat transfer coefficients and the fouling factors. So we can calculate U by that long equation. Now, another important thing is that for the case of delta T Lm, if you remember that we said that this delta T Lm is only applicable for pure countercurrent and co-current situation. But when you are talking about isothermal situation, it means that one of the fluid is pure. We can ignore, one of the fluid is pure and isothermal. We can ignore the value of Ft. The reason being because if the fluid is pure and isothermal, the value of R, that is T1 minus T2 over T1 minus T2. So this value will be 0 because the difference between the temperature on the shell side or on in the tube side, it would be 0 because you have isothermal conditions. Okay, and similarly for multiple passes, if you look at the value of Ft, you take the value of Ft as 1 because for the same reason, because the fluid is at isothermal condition. As such, the value of R will be 0. Okay, so it means that when we are designing condensers, we actually consider LMTD as our driving force. We don't need to apply the correction factor. So we have the value of U by this equation. Okay, so how it is different, for example, when we are designing a heat exchanger or when we are designing a condenser. So what is the difference? So when you are designing a condenser, and let's say you have condensation on the shell side, the thing that makes a difference is these two parameters, because we have to consider what is the fouling outside the tube, because that's where the condensation is happening. And also we have this coefficient H node that is on the outside of the tube. So we have to replace this H node, that would be equal to Hc. Okay, and this Hc is the parameter that we calculated in the previous slides. In most of the cases, F node and H node or HC, they are combined in one value for the case of condensers, because then you don't have to worry about what is the fouling factor outside the tube. Similarly, if you have condensation happening inside the tube, so we can use this formulation, but this time we don't have to change the value of H node because that is not important to us. Now we have to look at the value of HI, and the value of HI will give us equal to HC. Okay, so you have to choose depending on your scenario if the condensation is happening inside the tube or if it is happening outside the tube, and then you change the value of HI or H node depending on the scenario. Okay, so that is all for this part, and in the next part of the lecture we will talk about design of reboilers. Thank you for your time.